Hello all good people of the world, this is Paul Whittakin coming back to you with the universal law of numbers, and I'm going to kind of finish off where I left off yesterday. And I want to get this kind of... Okay. Maybe that's good. Okay, so what I was explaining was how the universal law of numbers can be expressed in many different ways, such as like this, or any of these kind of things, right? And that it's really all the same thing. And then I went ahead and I basically showed you how the universal law of numbers is, this is where trigonometry, calculus, geometry, and algebra come from. So obviously you can learn those subjects with the universal law of numbers. And more today, what we're doing is more algebraic. I would have to think it's, exponents and logarithms. And but it's also calculus. Calculus uses these x's and y's and z's and the whole thing to substitute for the number. And anyway, the universal law of numbers is a very easy design to understand how all of those numbers kind of come together, how they're arranged, and how we can actually use the universal law of numbers as a calculator. So I remind people that the universal law of numbers is the 369 code. It's going down 6, it's going up 6, it's going across 9, it's going this way 9. And it's got 3 sets of 9s, 1, 2, 3. And there's 6 in each of these sets. So we have the 369 code. And it manifests itself in many, many different ways. Literally infinite. So where I left off yesterday, I was doing the calculations going down, such as this, and we covered that a lot. But really, if you do this yourself, if you draw these numbers up yourself and start to look at them, I'm sure you'll find them to be very useful, you will get a very good grasp of what we refer to in this world of arithmetic, which is math, which is the study of the world, the universe we live in. So anyway, as we can see, we just get this. I'm going to show it to you a little bit differently this time. I'm going to show you it like the 369 code, and then I'm going to show it to you with algebraically with the numbers and the x's, represented as x's, and then we'll just do it with regular numbers, and we can start to recognize how the arithmetic all comes together. But anyway, 7 times 1 is 7, 4 times 1 is 4, 4 times 8 is 32, that's a 5, and that's just going to give us the 369 code. And the 369 code always gives us the 369 code because it always adds up as it has to. 7 times 7 is 49, reduces to a 4. For instance, 7 times 2 is 14, 1 and 4 is a 5, or 4 times 5 is 20. And 20 reduces to a 2. And we'll just do a couple more of these. And what we'll understand is if this system works here, then it has to work with these ones, and it also has to work with these ones. And it does, but it does it in its own very complicated, intricate way. But it does, and it always has, and it always will, because 5 times 7 is 35, and 3 and 5 is an 8. Then 7 times 4 is 28, which is 2, and 8 is a 1. 8 times 1 is 8. 4 times 7, 2 times 8 is 8. 5 times 7 is 35 is an 8. And now we're going to look at these numbers a little bit differently. Let me do it like this. Okay. Okay, now let's look at these numbers using this format. Well, what do we see? Well, basically what we see is, this is how we can learn how algebra works. 4 times 8 is 32, 3 and 2 is a 5. Okay, 4 squared times 5 squared Well, 4 squared times 8 squared is 5 squared. Well, it will reduce that way. It will reduce that way just like it does with the 369 code. But 4 squared is 16 times 64 is not 5 squared, which is 25. So we have to understand how that works. And we'll get to that, and I'm going to cover that. But anyway, here we have it. So we have 4 to the 8th times 5 to the 8th. Well, actually, that is 20 to the 8th. No. Yes, 4 to the 8th times 5 to the 8th would be 20 to the 8th. No, 20 to the 8th. 4 times 5 is 20. So it's 20 to the 8th. And 4 times 9 times 5 times 9 will be 20 to the 9th. So we have a 2, so now we have to understand how that works. But you can see that it is lining up. You know, the only difference between 2 and 2 quadrillion is the zeros. And we learn how to get the zeros from the equations. But in any case, if it's 4 times 9 times 5 times 9, it's going to be 20 times 9. Okay? And just, we'll understand that for the time being. 4 times 5 is 20. 4 squared times 5 squared will be 20 squared. Well, 4 squared times 5 squared will be 20 squared, and this is a 2 squared. So it's just one more zero, right? Because it's squared. All right, let's look at it over here. 2 times 8 is 16 is a 7. So one thing we can always understand that is going on, you know, 2 squared times 8 squared, it's going to be 7 squared in the sense that this is 149779419. So that's a 4. So 7 squared would have to be a 4, and that's what it's giving us. And we can just look and see how it's working. And I will get go a little bit more in depth about how it is working, but for the time being, let's just understand it in terms of the 369 code. 5 times 7 is 35. 5 to the 8th times 7 to the 8th is 35 to the 8th. 8, 3, and 5 is an 8, isn't it? Okay. Okay, what do we have here? Now we're going to start to kind of figure out how this thing works. In this case, we're going this way and it's coming around. So 2 times 5 is 10. 1 and 0 is 1. 2 squared plus 5 squared is 10 with, well, it's a 1 with 2 zeros, isn't it? 2 to the third times 5 to the third is 10 with 3 zeros. 2 to the fourth times 5 to the fourth is 10 to the fourth. So that's 1 and 4 zeros. 2 to the fifth times 5 to the fifth is 10 to the fifth, and that would be 1 with 5 zeros. Okay, so it's literally giving us the answer. So we can understand that. Now what we have to understand is that this 285396417, these are the codes, and they're the codes that are given by the 369 code, and they follow the 369 code with the exponents, and they follow the 369 code internally, and they work together. They're inverses of each other, reciprocals of each other. They're the reverse operation of each other, but they're always working together. Okay. So what do we have here? 2 squared times 4 squared, that would be 8 squared. And that would be correct. So this would all be conventional math. 2 squared times 4 squared equals 8 squared. 2 squared is 4, 4 squared is 16, 8 squared is 64, 4 times 16 is 64. So we can see it in terms of the exponents by adding them and getting the correct answer, and we can also do it in our head. You know, well, we can do it on our head to a certain extent, but we don't have to do it in our head because we understand that's how the algebra works. And that's a good thing, but we can be familiar with these numbers. There's nothing at all wrong with that. 16 times 25, that's 4 plus 2 zeros because it's on a 2. 4 and 2 zeros is 400. 64 times 125, that's 8 and 3 zeros, 8,000. 256 times 625, that's 16 and 4 zeros. 1,024 times 3125, that's going to be 32 with 5 zeros. Okay, what's going on here? I'm just showing you how that thing works. 4 times 25 is 100, and it's 1 and 2 zeros. 8 times 125 is, that's 1,000. 1 and 3 zeros, etc. 2 times 4 equals 8. 4 times 16 is 64. 8 times 64 is 512. 16 times 256 is 4,096. And reverse, 4,096 divided 256 is 16. 2,097,152 divided 16, 384 is 128. So all you have to do is basically understand the rules of the way it works, and you will soon learn that you can use this as a calculator to calculate very large numbers, and even in the realm of the, you can calculate things that are in the realm of the unknown, I would have to say, because it's not exactly clear. I don't think everything that there is about this has been discovered or uncovered. So now let's do it with real numbers, and we'll go 256 times 125. Okay, that's 3,200. Because we take it from x to the fifth over x to the third is going to be x squared, and that's how we get the 32 with the 2 zeros. Okay, let's see how this works. Now it's sort of going backwards. We're going in this direction. But anyway, 4096 times 78,125, which is 5 to the 7th, is going to be 32 with 5 zeros. It's right here, 5 zeros. $256 times 3125 will be 1, 2, 3, 4, 5. It's determined by this 5. It's going to be the 8, the coefficient is determined here, and the number of zeros is determined here. And that's the system, how that works. And actually, I broke down the system, and I'm going to show it to you at the end to show you how simple it really is. But to know that it's simple, it can be simplified, is a very powerful thing. But to actually know how these numbers work together is that's a very powerful thing too. And if you're able to do this kind of arithmetic in your head, that becomes very powerful too, because what you're doing is you're doing calculus and you're doing algebra, and we know that those are very powerful tools. Now, what we can do is we can do a little algebra. For instance, 8 is 2 to the third, 16 is 4 squared. That's simple. But when we multiply 2 to the third times 4 squared, it's not the way it's going to work in algebra, because we need to get either the coefficients to be the same number or the exponent on top to be the same number, and then we can do it algebraically. But anyway, 2 to the third times 4 squared is the same as 2 to the third times 2 to the fourth, because 2 to the fourth is 4 squared. And then we get 3 plus 4 equals 2 to the 7th, which is 128. And we can do a couple more with the numbers, because then you can see how these numbers multiply and divide by themselves to come up with themselves, just like the 369 code does. The 369 code works when we multiply or add or whatever, codes by codes, and these numbers are in fact also codes. But anyway, what do we have here? So 4 times 16 is 256. And now 4 times 64 is 256. 16 times 1,024 is 16,384. And I think you can see that there's a pattern emerging there, and there is. I actually guess I can show it to you on this one. Well, that's not exactly the same pattern, but here it goes directly to here, and here it skips. Well, that is the same pattern. So you can see 4 times 16 is 64, but 16 times 256, skip 1, is 4,096, where 64 times 4,096, skip 2, and you're going to get 262,144, which is this number right over here, and it is 8 to the 6th. Which that works algebraically, of course, as well. Okay, just very simply, now you can see we're doing some of this. You see what happens, the direction makes all the difference, because that determines the rules. Now, 16 times 64, that's 2 to the 4th, because this is 2 line, and this is 4 line, and this is 4 squared, so 4 to the 3rd. So 2 to the 4th times 4 to the 3rd will be 1,024, which is 4 to the 5th. But the way I did it was I said 2 to the 4th is the same thing as 4 squared. So this is a very helpful thing that people do in mathematics. If they understand that you can change, the way you write the number, it's the same number, but then you can solve the equation. Well, that's a big factor in solving mathematical equations for sure. So now what we do understand, and I'm going to show this very soon because it's sort of what it's all about in a sense. The way that the 3, 6, 9 numbers work together in tandem is one set of rules, and the way that the 2, 4, 8, 7, 5, 1 numbers work together, they have another system, and that 3, 6, 9 system is found here too, because this is an x to the 3 and this is an x to the 6th. Those are the 3, 6, 9 rows going across, whereas these are 2, 4, 8, 7, 5, 1. So that's why the 2, 4, 8, 7, 5, 1 code is the 3, 6, 9 code, and the 3, 6, 9 code is the 2, 4, 8, 7, 5, 1 code, because in a sense, even though they're the same code, you could literally treat them as different codes and you'll get the same answers. Okay, 2 times 4 is 8, fine. 4 times 16 is 64. I think we've done one of those. That's the simplest way to show it. 16 times 64 is not going to be 4. Now, is it? No, it's not. But reversing it, you can see that it's going in this direction. It is working, because 64 divides 16 is 4, and 512 divides 64 is 8, and 4,096 divided 256 is 16, and it's working because 4 times 16 is 64. And okay, so I'm overstating the obvious, but what I'm doing is I'm overstating the obvious over and over and over and over and over so much because I want to I guess I want verification for myself, confirmation always for myself that the thing actually is a reality and it's not some figment of my imagination. But anyway, the same thing applies here. Now, if we were to do this, 5 times 7 is 35. Very good. 3 and 5 is 8, and 8 squared is 64, and that's fine. In any case, this is a 1, because 6 and 4 is a 1. Now we'll just look at it a couple more, and then we'll do some going this way, down and across, and we'll see if we learn something from that. But anyway, 2 times 8 is 16, and 1 and 6 is a 7. So we know those numbers will reduce, but it's not doing conventional math. That's just the 369 code. And the same thing will apply here. This is a 7, so 16 times 64 will reduce to a 7. And that's all we really care about in that instance, because doing all of these, doing the arithmetic, it's not as important to understand or memorize an answer as it is to recognize the pattern and see that the pattern's working from a distance, understand that the pattern is there, the whole thing's working, and then you just go in there and you figure it out out all for yourself, which I highly recommend you do. 4 times 9 is 16. 4 times 9 is 36. 36 divided 9 is 4, so these are going to go back and forth, and they're going to be perfectly fine, and they're following the rules for conventional arithmetic. Okay, now we're going to look at a couple, just some of these at the end. 64 times 64 times 25 is 1600. So 16 with 2 zeros. The zeros come from here, and the 16 comes from here. So the coefficient comes over here, but the exponent comes from here. So it's 16 with 2 zeros. And we'll see it again. We're doing the same kind of thing here. Here we're going in this direction, 64 times 625. Well, that's going to be, I'm going to have to assume it's 4 with 4 zeros, 40,000. Because here we get the zeros and here we get the exponent. Okay, so now I'm just going to finalize it by, I'm going to show you how this works with the 248751 code, and we'll leave the 369 code to the next time. But basically what goes on is it establishes a pattern. So here we have the 2's establish a pattern that's increasing by 8s. 8, 16, 24, 32, 40, 48. That's increasing by 8s. Now, here I take it out to 512, okay? So we see that the 2's and the 4's are similar to the 8's, aren't they? Because everything that is divisible by an 8 would be divisible by a 4 and a 2. Anything that's divisible by a 4 would have to be divisible by an 8. But anyway, it gives us the code. So these are increasing by 8, the 2 numbers. The 4 numbers are increasing by 4. 4, 8, 12, 16, 20, 24, 28, 32, 36. The 8, this is 2, 4, right. The 8 numbers, this is 8 numbers here. Okay. Anyway, they increase by 8 as well. 8, 16, 24. 32's 8. We'd have to go to the next page of that, which is this one. And we can see that it's 8, and then it was 16, 24. And 64, which is, okay, so 248751. This is 248, 16, 32, 64, 128, 256. 248751 is doubling. So I'm taking it out and I'm just doubling these numbers, and we're seeing what kind of pattern arises. With 128, it takes 128 to the 8th to be equal to 4 to the 28th, which is something to be equal to 5 to the 2 to the 56th. What we see here is basically here we can see it. Let me just put this up here for a second. Okay, well, anyway, what we're going to see is as we take this out further and further and further, it's still going to give us the same exact diagram. So here it starts at 2 to the 8th to the 2 to the 72, 2 to the 80 to the 2 to the 144. Here it's 2 to the 152 times 2 to the 216. And no matter how many pages of this we would do, on and on and on, just like the 369 code, universal law of numbers, it will always come up with the same pattern, which is this pattern. And you can see how the 2's and the 4's work together. You can see how the 2's and the 4's work together with the 2, 4, 8, 7, 5, 1, 2, 4. That's the 4 again. So that's what's going on there. So that's the 4 again, because 2 and 5 is 7, and 6 is 13, and 1 and 3 is 4. And now we have 512, and it takes 9 times, or 2 to the 72, which is 9 times 8, because the 2's are increasing by the exponent of 8 to get 512, which is a perfect anything. Okay, so the last thing I'm going to show you today is I'm going to basically, the thing that I say needs to be somewhat backed up So what I'm saying is that the 369 code, that with the 369 code, the universal law of numbers, as we know it to look traditionally, and we'll find one here. I must have one here somewhere. Shouldn't be that hard to find in my world. Well, they're all the 369 code. All of these things are. It's true. But I want to show you in the traditional form. It's probably right here in the beginning. That's fine. Okay. So that's a good one. That's the 369 code. And we'll show it with the exponents. That's even better. So that's the 369 code, the universal law of numbers code. And what I'm saying is that these exponents, they're following the 369 code as I demonstrate when I show it to you like this, because it starts at 2 squared, going to the 2 to the 7th, then it's 2 to the 8th, times 2 to, then it's 2 to the 13th, and now it's 2 to the 14th. So 14 is 1 and 4, and it's a 5. So 2 plus 6 is 2 to the 8th, plus 6 is 2 to the 14th. 2, 8, 14 is 5. 2, 8, 5. Here's 396, 417, 528, 639, 741. Okay, so what I'm saying is those exponents, they create the 369 code just like the 369 code creates the 369 code, and this is an inverse of this. Let's say it's a mirror image of it, but it's certainly always working together the same way. And I'll show you why I say that. So I go, here I'm going to do it the exact opposite. I'm going to take 149,779,419, and I'm going to bring that down on this side. So it's x to the 149,779,4, and that continues, and I have it. 149,779,419, and on and on and on. So we're going 149,779,419 down that side. So let's see what happens to those. All we have to do is multiply that exponent by its reciprocal, and it will come back to 149,779,419. And multiply x to the 9th by its reciprocal, and now it's 1 to the 3rd, 2 to the 3rd, 3 to the 3rd, 4 to the 3rd, 5 to the 3rd, etc. So that's what I am attempting to demonstrate to you with that. And that actually also gives us a matrix, because we can reduce those numbers as I always do. And it shows you the 369 code, because the 369 code is really 1, 2, 3, 4, 5, 6, 7, 8, 9. But if you cut it off at position number 6, it goes, let's say 9, 8, 7, 6, 5, 4, 3, 2, 1, 9, 8, 7, 6, 5, 4, 3, 2, 1, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's repeating, which is the 369 code, because it's the codes 285, 147, 396, 285, 147, 396. And we see we get it here too, and we see we get it here too. But what do we get over here? We get 8, 7, 6, 5, 4. And here it's 5, 6, 7, 8, 4, 5, 6, 7, 8. Very interesting. With the 4, it starts off a little different because it has to get into the rotation. If you didn't quite pick up on that when we were going over it, basically 4 doesn't start its pattern until it gets to here. And then when it gets to here, then it repeats to infinity like this. Okay? That's all. And always remember that inside of this universal law of numbers, by condensing and condensing and condensing, we get a very broad understanding of how the whole system works together. And it's very important to understand that what I was just doing today, as it applies to the perfect squares and also the perfect cubes and how they all apply to each other, these are very important numbers that work together in a very specific way. And the perfect squares will always reduce to that, just like the universal law of numbers will always reduce to what it reduces to, which we know what it reduces to. And basically these perfect squares and these perfect cubes, etc., 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 they are the frame, they're the framework of the building. They're the framework of the building. And as you can clearly see, and is quite logical, they're the same numbers we were dealing with today. And those numbers, they will always just do that, the same numbers. We just increase the exponents, but they can remain the same numbers forever and ever and ever, or we can change the coefficients and we can make the exponents smaller, but they're always going to be the same numbers. And this is Paul Wittekind coming to you today with the universal law of numbers. And I'm going to quickly check how much time. Okay, I'm going to take just a couple minutes maybe to go over some things that I'm trying to get across. Okay, but anyway, we recognize that we were learning algebra today by doing these lessons. I think that's pretty clear. To me, it's clear. Now, what I'm doing here is I'm basically showing you a game, and this game is very fun to play, but the result of learning how to play this game and being proficient at this game will make you more knowledgeable and proficient about the universe in general, and certainly mathematics and certainly numbers, you know, because if you increase your aptitude just with understanding how the numbers multiply and add to each other and fit together, well, the whole subject of math becomes much, much easier. And that's what the 369 code does for us. And this comes, you know, it comes from way before people had any other way of learning mathematics. So I've never seen this anywhere before, but I would have to assume that people in the world must have used this to develop the mathematics, you know, that we have today. Okay, so we'll just kind of, we'll leave it at that. That's sufficient for one day. So this is Paul Wittekind, and I am signing out, and I wish all good people of the world peace and happiness. Until next time.